Thanks to FINRA for giving us this opportunity to come in and sponsor this and also support this. Just came back actually this weekend. I was in Carnegie Mellon in Pittsburgh, attending a hackathon. So this is kind of like a hackathon, Createathon, week looks like. I'm just going to briefly, give you a little bit of background on CompuGain. Some of you guys might have come across our consultants, and then I will, give a little bit of, fun facts on our, culture, what we're trying to do with CompuGain Solutions, how we're kind of aligning ourselves with FINRA in terms of some of the areas of focus for us, and then, I'll introduce our keynote speaker. Just quickly, from overview perspective, CompuGain, we've been in business for 17 plus years. We've had a 10-year partnership working with FINRA. We've been involved in a lot of your critical projects. I think you can see the list there on the screen. And I think we consider ourselves to be very fortunate to be working with FINRA, working with a lot of creative people, creative culture, culture of innovation. From our perspective, we've been focusing on building some centers of excellence, centers of innovation, and our focus areas are kind of aligned with what you guys have been doing for a long time. Cloud, DevOps, microservices, big data analytics, machine learning, deep learning. From a vertical perspective, we have focused on BSFI, finance, banking, insurance, and then also healthcare. At the bottom, you see, we're partners with Amazon. We are partners with Lightbend on the microservices side. We have a number of other partnerships. We are heavily involved in the ecosystem in terms of advancing and bringing new technology solutions to our customers. Just a few things we think we share with FINRA, in terms of our outlook on what the culture, and from a CompuGain Solutions perspective, like I said, our centers of excellence, we kind of do the 80-20 culture, 80% of the time on structured assignments, and 20% we allow our engineers to focus on bringing some disruptive things to the table. We participate a lot in meetups. Recently we were part of a Capital One, microservices meetup. And then, like we mentioned, we have a lot of focus around centers of excellence in the areas we already talked about. So we're doing a lot of work around machine learning and, using R, Scala, Python. So we have a collection of data scientists who are looking at this. A couple things, what we're doing that's we think is exciting. One is, there is a new regulatory, requirement for very large banks. It's an FDIC requirements for qualified financial contracts. So we are, it's basically involves automating a supply chain, kind of looking at shared assets, tracking them, with third parties for banks. So we are using blockchain and IoT, for doing some of that. And then lastly, I just want to mention a couple of, really exciting things we're doing. One is, the bank in a box. This is basically a digital bank, that's addressing the gig economy. So, like the Lyft and the Uber and a lot of consultants, workforce. We're, basically building, the next generation bank, I would say the digital bank, and integrating with a lot of data sources using APIs like Yardley and things like that. So we feel it's a great, fintech work that we were fortunate enough to do. And then lastly, the digital transformation, wealth management. The wealth management space in the banking sector has always been kind of lagging. So, we are bringing some machine learning algorithms for customers in terms of micro-segmentation, some really interesting, UI in terms of user experience, using emotion recognition APIs and, to assess risk profiles. So there's some really good work. And we're also using NLP to, kind of gather what's going on in the financial markets, being able to, bring that, to do portfolio recommendations in wealth management. So we feel like it's a great opportunity for us to apply the technologies that we're pursuing with our centers of excellence. So that's kind of like a brief background on CompuGain. And just wanted to take a couple minutes to introduce our keynote speaker, Jared Lander. He's the CEO and founder of Lander Analytics. He's also a professor at Columbia, and he's very active in New York statistical programming. He runs the meetup and the conference, the R conference, author of several books. But a couple of fun facts. Jared was involved in the the draft, NFL draft with the Minnesota Vikings, and also heard his PhD thesis was on picking the best pizza place in New York. So I'll let him talk more about that. Jared.
All right, thank you very much. Can everyone hear me? Wonderful. Thank you for that introduction. Thank you, everyone, for having me here this afternoon, or this evening. Well, we'll still call it afternoon. It's still early enough. I'm very happy to be here. I'm a big fan of your mission. We've actually been involved with FINRA for about a year now, and we really enjoy working with you folks. So again, it looks like there's going to be a fantastic time, an amazing Createathon, and it seems like just going to be a great time. So really enjoy the next few days. So as briefly mentioned, I am the chief data scientist of Lander Analytics. Can people see my slides? Some of you are saying yes, some of you are saying no. There you go. Wonderful. OK, they're mostly aids, though. There shouldn't be a lot to read, so enjoy the pictures. We are a data science consulting business. Everything we do is all about data science. We do strategy, research, implementation, training, and industries all over. Banking, retail, pharmaceutical. And we tend to be mostly an R shop. That's because I'm obsessed with R, as I'll show you in a second. We do other languages. We do Python, Julia, SQL, C++, whatever we need. But we tend to focus on R because of my personal leanings. It's because I'm a professor at Columbia University, where I teach data science and R. I'm the organizer of the New York Open Statistical Programming Meetup. It's a long, terrible name. It used to be the R Meetup. But then before I took over, the organizer at the time, Drew Conway, changed it to the Open Statistical Programming Meetup to show that we're inclusive. And we are. We allow meetup, we not allow, but we bring in talks about Python, about Go, Julia, whatever language suits the needs for that month, we bring in those talks. It tends to be majority is in R, but not all of it. And as mentioned, the New York R Conference. Again, that's open. We allow other technologies in there. We have Python talks. We have Julia talks. We have just data science talks. But the focus is on R. And as part of the community stuff, this has nothing to do with my company. We support it by doing the labor. But it's an open source community-driven event. And the meetup, I'm very proud to say, is the largest R-focused meetup in the world, of almost 9,000 members. I do know down here in DC, there's a similar one called DC Stats Programming. It's an amazing meetup. The community is so great. And my obsession of R continues. For those of you who don't know me, I wrote a book about R. This is a plug. Everyone should go to Amazon right now. No. But this clearly is a language. And the reason I love it so much isn't just because I think it's a fun language, though I do. It's because it's meant for data. It's meant for statistics. It's not a general purpose language that can also do this. It is meant from the ground up to be for statistics. And I'm a classically trained statistician. I'm a good old-fashioned nerd, love math class. I could talk to you about Chebyshev's inequality, about convergence principles, about Pearson. We can go on and on and on. That's my background in statistics. But of course, that's not good enough. So today, I am a data scientist, which is much cooler. Everyone agrees that data science is much cooler than statistics, right? Even though they are pretty much the same thing. And I say this as someone who teaches data science academically. So to illustrate what a data scientist does, we are required. We must show this Venn diagram. You cannot go to a data science conference without seeing this at least 8 times. It's a rule. Now, I'm very proud. This is my friend Drew made this. And when he made this, I think it was just late at night one time. It's like, I want to make a cool Venn diagram. He had no clue this would come on and take a life of its own. But it does sum up what we do pretty nicely. You have your math and stats knowledge. That's very important, knowing when to use what algorithm, when to use which model, how to do it. Your hacking skills. Whenever I talk about hacking skills, people are like, oh, you're a hacker? I'm like, different type of hacking skills. You need to know how to program. You need to use a computer. You can't be using GUI. You're doing something programmatic. Saves you time, gives you creativity. Life just gets so much better. And of course, your substantive expertise. You have to know what you're doing. If you're fitting a model, you need to have some sense of why you're fitting the model, how it's happening. That's very important. And we all know we are in the right field because this is the sexiest job of the 21st century. Now, this is a nice article. It came out from the Harvard Business Review, written by Thomas Davenport and DJ Patil. Thomas Davenport was the chief economist at Google. And DJ Patel, at the time he wasn't, but he then became the chief data scientist of the United States. Talk about a title, right? And the field's blowing up. But now even data science isn't cool enough anymore, right? We all know that we need to do AI, right? This is the new sexy. This is what you have to be doing. Now, before we get swept up in all the hype, because there's a new article like every 3 hours, right? You're constantly seeing Forbes, Medium, everyone's writing articles, AI, AI, AI. Let's break it down a little bit. I was fortunate enough to give a talk at Lincoln Center last year about AI. It was actually for filmmakers, so it was an interesting talk. And I managed to steal a quote I read earlier that day that said, worrying about AI taking over the world is like worrying about overpopulating Mars. We're very far away. And now that we have this new buzzword of AI, we need a new Venn diagram. Now, this comes from an amazing book called Deep Learning. It's written by Goodfellow, Bengio, and Corville. I highly recommend this book. I say it's one of the best machine learning books I've ever read. And it's up there with elements of statistical learning in terms of the landmark status. And they make a very good point that AI is this encompassing computer knowledge, and that machine learning is just a subset of this knowledge. And that's your logistic regression, your linear regression, your decision trees. And within machine learning, deep learning is a subset of that. So it's very important to think about what we're doing. And I like to think of deep learning in particular as extreme nonlinear modeling. And we'll talk about that in a little bit. But since we're going to jump into the marketing, what is AI? I find a great definition, which I also stole, is what humans find easy, but computers find hard. And this is a moving target. It changes over time. But what's going to be really amazing about AI is the senses, seeing, hearing, the things that are so intrinsic to humans that come naturally. Making a computer do this is going to be amazing. And true AI will be a combination of models and algorithms. You need a model to model the world, but you need an algorithm to learn that model. So why now? Why is AI so big? It was big before. We've seen hype about AI before. What is so different about today? Well, first up is the old buzzword, big data. We have so much data. Our capacity to store data doubles every 10 months. Contrast this to Moore's law, which is hanging on by a thread, that our compute power doubles every 18 months. That means our ability to store data is outstripping our ability to process data. Let's sit in for a second about how much we have. To use all this big data, we need hardware. Anyone who's ever been to one of my conferences has seen this little device before. This is called a hex. There are 6 computers networked together into a cluster. This one is called R2D2. That's because it is literally held together by a 3D printed piece of plastic. It has each machine, each computer on the side of the hex has a few cores, 8 gigs of memory, and a terabyte of disk. And this thing sits on my desk. It's little. It's a little guy. And I got this in 2014. 3 years ago, I had what is essentially a little supercomputer that sits on my desk. Now, this supercomputer is awesome and it's fun. But let's talk about a real supercomputer. This is the NVIDIA DGX-1. I'm not sure how many people have heard about this, but we're partners of NVIDIA, so I get a chance to play with these things. This has 960 teraflops. I should say it performs 960 teraflops. A teraflop is 1 million floating point calculations per second. This can do 960 million floating point calculations. It accomplishes this with over 40,000 CUDA cores. 40,000 cores in a single machine. And it has over 5,000 tensor cores. You have a lot of processing power. Of course, it doesn't come cheap, depending on your definition of cheap. This costs about $150,000. So for a big organization, that's not outside the realm of possibility. Especially for a big government agency, if they need to do some complex modeling, they can get this. Compare this to a Cray, how much a Cray is going to cost. And of course, you could split this up amongst different people. They each get 10,000 cores or 5,000 cores. Or you could have one programmer fitting a ginormous model. So now that we have all this great hardware, we need to program it. And of course, if you're going to show code in a presentation, it has to look like a 1980s hacker movie. The software availability is just amazing now. We have so much software available to us. If there's something you want to do, odds are it's been written already. And if it hasn't, individual components have, and you just have to stitch them together. Some of these models have been around for a while. Some are newer. And I'm just going to walk through some of my favorites and some of what are hot right now. First up, and this has been around for about 10 years, is GlimNet. This is an implementation of the elastic net, which is a form of penalized regression. It's a combination of ridge and lasso. Other words for those are L2 and L1. So you don't have to choose anymore. Do I want an L1 penalty? Do I want an L2 penalty? You can have both. And it changes the behavior and changes the results. This is really great where you have a lot of columns, possibly even more columns than rows. It performs shrinkage and eliminates columns for you. And also shrinks them towards 0 so you have better predictions. And the amazing thing about this modeling algorithm, which can do Gaussian, can do binary, can do Poisson, can do multivariate normal, classification, Cox-PH. It's all written in 73 lines of Fortran. That's all it takes. It's amazing what they accomplished in such a little amount of code for a very verbose language. Now, this is still a linear model, which means it's explainable, but might not have as much power. So we can talk about XGBoost. This does extreme gradient boosting. Now, it's designed for and is primarily used for boosted trees. But it also does boosted generalized linear models. So in case you still want your model to be linear, you can use the XGBoost software to fit a boosted linear model. This has revolutionized the field of predictions. The predictions you get out of XGBoost are amazing. And even better, it's incredibly fast. This is one of the fastest algorithms out there. Now, there is another library called LightGBM from Microsoft, which is supposed to give it a run for its money. In case you're a Bayesian, there's Stan. This allows you to run Markov chain Monte Carlos so you can fit your model through simulations. This is put together by Andrew Gelman and his team. He's my former professor, so I have a sweet spot for Stan. And this is used for what they call big models. Not necessarily big data, though. You can use big data when you have a complex model with a lot of features, and you want to capture all of the complexity of your data generating process. It's a really great tool. It's a domain-specific language that you can call from R, Python, Julia, the command line. You can even call from MATLAB. I don't encourage using a closed source tool, but you can. And then, of course, what's getting all the excitement now, deep learning. Everyone's very excited about this, but let's keep in mind, these are just neural networks, all right? And neural networks have been around for a very long time. I think they came around in the 50s, and they were very cool. Then they weren't cool. Then they became cool again. Then they got lame again. And now they're cool once more. All right? It has definitely ebbed and flowed. Remember, it is just extreme linear modeling. I'm sorry, take that back. It is extreme nonlinear modeling. It's a form of many nonlinearities that come together to make a really good prediction. And there are many ways you can implement modern neural networks. Probably the one with the most market share is TensorFlow. And TensorFlow is a great name, by the way. A tensor is just a multidimensional array. It's a mathematical term for a multidimensional array. If you took a matrix and expanded it into other dimensions. And they are flowing that through a computational graph. Great, great marketing. Now, if you go down the street in Silicon Valley, you have Cafe 2 from Facebook. It's another great tool for fitting neural networks. Well, go up to Seattle, and we have CNTK from Microsoft. Go down the street in Seattle, and Amazon is pushing MXNet. And even Sony has made their open sourced their deep learning package. It's called Nabla. All these companies are tripping over themselves to give us open source software. It's not only free, it's open source, meaning you can see the code and contribute and change and hack away at it. We're all winning from these giant corporations competing with each other. It's pretty amazing. Some of these companies have something to gain. None of them are trying to push consulting time to give you a complicated piece of software, we'll do consulting. Some of them are pushing hardware and compute, but not all of them. Some of them are just releasing them so they can be cool. And that totally works for us. But in case you don't want to get into the weeds of one of these frameworks, there's Keras. Keras, whoa, that slide is really off the slide. All right, well, it's showing the Keras logo. Keras is an abstraction layer that lets you code once and switch the backend framework to be another platform. As of now, it works for TensorFlow, Theano, and CNTK, and they've announced support for MXNet. So you have your choice of different frameworks all using the same code. And what this is doing is bringing deep learning and ML to the masses. It's all open source. So anyone with knowledge can now go fit ML models or even deep learning models. It has gotten so easy that there is an app available for Android and iPhones called Not Hot Dog. Now, I assume a lot of you have seen the HBO show Silicon Valley and know that Jin Yang accidentally developed an app that could detect hot dogs, which actually has a lot of applications on online platforms for other reasons. But this is a real app. An HBO developer who had no prior training in machine learning or AI or data science spent a few months with a laptop and an external GPU and built this app. You can go to the store and download it right now. With just a few months of no experience, they built a computer vision app that runs on a phone. When I say runs on the phone, I don't mean it takes a picture, sends it to the cloud, and then sends you the result. It actually computes on the phone and does the inference right there. This is amazing what can happen by one person with these tools. So what can we do besides have a lot of fun? I have a few use cases I'm going to walk through that describe some interesting ways you can apply this technology, whether it's ML, DS, AI, or any other two-letter acronym. We are in DC, or near DC, so we should have three-letter acronyms, but we'll stick with two. So let's suppose you work in finance, and you want to do anomaly detection. Perhaps there are thousands of trades being processed every second, and you want to catch weird trades. Now, weird can mean mistakes, can mean bad decisions, even fraud, right? Let's say you want to look at the trades, find the ones that are suspicious, and flag them for a human to look at. You don't want a human to look at all of them. They couldn't. You want to have just a subset, so you can save a lot of time and money. Really, what this boils down to is looking at the tails of a distribution. That's all it really is. What falls outside the bounds of normality? And I don't mean necessarily normality in terms of the Gaussian distribution. I mean normal behavior. For those wondering about this, this is actually a new plotting library called Vega Lite. It's a very cool library. You write it in JSON, and it computes in the browser. And there's an R package called Vega Lite, which will let you generate this. In one dimension, it's very easy to see what's in the tails, right? Very quickly, easily see that. But what happens when there are multiple dimensions? When you have many, many characteristics? We need to model this. And even a simple linear model will do. We'll start with just a straight-up Gaussian model that's centered at x beta with sigma for the standard deviation. The goal is to have some output value. Maybe it's a notional amount. Maybe it's volume of trades. It could be any output amount. And you want to find characteristic behavior conditional on all the other characteristics of the trades. This could be time of day, day of week. It could be who they're trading with, the number of legs. It could be any number of things. And the goal is to get prediction bounds. So we're going to use linear regression because it easily gives us prediction bounds. You can do this with XGBoost by predicting quantiles, but we'll stick to this. So the goal is a trade comes in, and you make a prediction based on all of its characteristics of what the value should be. Whatever output value you're looking at, you're making a prediction for. Again, whether it's a notional amount, whether it's volume, whether it's value, whatever it may be. You make a prediction. You then compare the true value for that output to your prediction. If it falls outside of these confidence bands, it needs to get looked at. If it falls inside the confidence bands, you can let it go. And it seems, oh, look, that's outlier prediction. Well, you really have to fit a really good model to make this work. Because you need to balance the cost of intervention with the cost of a failure to intervene. So maybe you shouldn't be optimizing on how out of bounds it is, but you should be optimizing on how out of bounds it is, coupled with how much it costs to investigate or not. Another example, which has nothing to do with finance, is football. As mentioned, we were engaged by the Minnesota Vikings to help them with their draft. They have small data, all right? I got there. They're so excited about how much data they're going to give me. They gave me 700 rows. We had to get very creative. So in order to do this, we couldn't just fit one model. We fit hundreds of deep learning models and built an ensemble that combined them all, because that was the best way we could wring out all this information out of there. Now, the draft was highly thought of. Gil Brandt, the godfather of sports analytics, said we won the draft that year. Sports Illustrated gave us an A. They had 10 picks. 8 of them made the team, which is really rare. Of those 8, 5 got regular playing time, which is unheard of. And of those 5, 3 became starters that year, which never happens. So we're very happy with this. But it's important that the machines weren't there to replace the humans. They were there to augment the humans. And there was a former linebacker who made me remember that at every meeting. Now, of course, a lot of what we did for the Vikings is special stuff. I can't tell you how I did. But I promised I would talk about football. So instead, I'm going to talk about the New York Giants. They had a bad week last week. That's OK, because we're not here to talk about last week. I want to fit a model, and this could apply to any team, actually, about whether they're going to pass or run the ball on a given situation. This is adapted from a talk I gave at the MIT Sports Analytics Conference. And the goal is to figure out whether Eli is going to throw the ball or he's going to hand it off. Now, you would do this if you were an opposition defense. You research the team you're playing, and you want to know their tendencies. So let's just look at the overall pass versus rush. And we see that Eli passes a lot more than the team rushes. This makes sense because Eli is really good. I know a lot of people like to make fun of Eli, but he has 2 Super Bowl MVPs. That's more than his brother has. And he's still the only person to beat Tom Brady in the Super Bowl. Twice. And he holds a lot of records, so it makes sense that he's going to pass a lot. But let's break this down a little further. Let's look at it by down. On first down, passing and rushing hits about parity. By second down, then third down, he's throwing the ball a lot more. And on fourth down, there's not a lot of data. And we see a pattern. We can just go tell the coach, oh, yeah, on first down, I don't know. On second and third down, they're going to throw it. We need more nuance. So we're going to fit 3 different types of models. The first is a binary regression. You might call this logistic regression, but that is technically incomplete because there are multiple types of binary regression, the most popular of which is logistic. But everyone knows these equations, right? I won't even explain them. These are estimating the probability of a pass. And it's accomplishing this through iteratively reweighted least squares. It's just fitting a Gaussian linear model repeatedly and adjusting the weights until it converges on a minimum. And when you run a linear model, you can get results back in a nice coefficient plot. And this coefficient plot shows you a point estimate for the estimate for a specific variable and confidence intervals. Now, I know confidence intervals are highly controversial. And they could even be doing a lot of damage because not confidence intervals directly, but they're essentially the flip side of a p-value. And p-values are very dangerous. Even John Oliver had a talk about p-values. He spent 15, 20 minutes on a show talking about p-values. We're not talking about them today, all right? But this very quickly shows you that the higher the down, the more likely they are to pass. And I included a variable for yards to gain. And the more yards to gain, the more likely to pass. We can make sense of this chart and derive some inference from it. But a coach on a playing field needs to make a call in just a few seconds. And the coach cannot be sitting there looking at this chart trying to figure out what to do. And also, the coach is not allowed to have a computer. In fact, the coach is not even allowed to talk to anyone who has a computer for 2.5 hours before the game. No computers allowed whatsoever. So we need to visualize this in an easy, digestible manner with a nice, simple plot. You could print this out, laminate it, hand it to the coach in triplicate, and very quickly you can flip and say, hey, what's their situation, and know what the offense is going to do within a degree of uncertainty. And we can quickly see that on first down, Eli is more likely to hand the ball off. Then on second down, more likely to throw. On third down, even more likely. And on fourth down, it's a mixed bag. And part of that is because there's not a lot of examples. Of course, if we were really doing this for game time, we would take into account field position, score, time remaining, weather conditions, so many more variables. But for a simple illustration, this works. But we also see that this is monotonically linear. It might not have complete information. So let's try a decision tree. A decision tree is a nonlinear model, and it has higher capacity. It can get more nuance in there. And as you can see from this equation, it's a very simple model. You essentially break up your data space into lots of discrete little regions that don't overlap, and take an average in those regions. You can get fancy and take a regression in those regions, but it's really just an average. And if it's a binary outcome like this, it's a vote. How many passes divided by the total number of plays? It's actually a really simple algorithm to conceptualize. It used to be hard to compute, but now it's really easy to compute. In fact, so easy to compute, we're going to skip decision trees and go straight to boosted trees. Now, boosted decision trees iteratively build up model after model. It takes a bunch of weak little tree stumps and stacks them into one powerful model. And this gets incredible results. It has amazing predictions with low variance. So you don't have wildly swinging predictions. Of course, boosted trees aren't as easy to visualize as single trees. But we're making progress. Whoa, too many slides. We're making progress on this. This is a collection of about 500 trees compressed into one visualization. And it gives you an idea of where the splits took place. But you have to look at it holistically. You can't just sort of get anything deterministic. You have to holistically look at it. But that's OK, because it gives us a lot of power. And running our scenarios, it now looks like this. It is a lot more wiggly. And believe it or not, that's actually a technical term. Wiggliness is a technical term to describe how not smooth your curve is. Now let's break this down a little bit. First down. There aren't a lot of first and short plays, except for maybe first and goal, when you want to just pound it across the goal line. So of course, then they're going to be more likely to run. But it's weird. It spikes around first and 6. This is probably because it's after a penalty, it's first and 5. You're going to catch the team off guard throwing a pass. And then it roughly stays close to 50%. On second down, as we expect, short yardage you might run, but as it gets longer, you're going to pass the ball. Third down. 3rd and 1, you're most likely going to run. But very quickly, by 3 yards to go, you're passing the ball. And 4th down is even more dramatic. It has a big spike. After 4th and goal, 4th and short, you're throwing that ball if you're doing anything at all. All right. Let's do this one more way because we can. Neural networks. Everyone loves it. I heard a woo. Nice. Now, there's no quick little easy formula for neural networks, so I don't have any math to show you. I know everyone's highly disappointed about that, right? But this is a computational graph. And this is for a 2-layer network with 256 hidden nodes and 128 hidden nodes. We're using dropout and batch normalization to perform regularization to constrain the model a little bit. This is a little harder to code than XGBoost, but not a lot harder. And it is slower than XGBoost, but not incredibly. Of course, we could speed this up if we threw it onto a GPU. But for this model, I ran it on my laptop, and I've ran it dozens of times. It doesn't take that long. So let's check out the outcome. Vastly different results. So first of all, it's a lot smoother. Second of all, on first down, they're saying it's a pass play almost no matter what. And then it's nice on second down, it is increasing. On third, we sort of see that spike. And on fourth, we see that spike. Which model was right? We'd have to test it, fit an ROC curve, and we could do that, but I leave that as an exercise to the user. Moving away from sports, I want to talk about network analysis. Network analysis is a really powerful tool. But before I talk about that, I want to talk about this graph. This is actually a live graph. If you take my slideshow, it's an HTML file, you can take your mouse, drag that graph around, zoom in, zoom out. This has about 4,000 nodes and 80,000 edges. And it rendered in less than a second on my laptop in the browser. This is a package called 3JS by Brian Lewis that is built upon the WebGL package of the same name. He demonstrates this on a $300 Chromebook. And it renders in less than a second, 80,000 edges that you could drag around, zoom in, and have more information and click on it. It's really amazing. But a particular application for the folks here might be using network analysis to figure out who is talking to whom and about what. This is a project that, unlike many of my other clients, they instructed me to make it open source. It is available on GitHub, all my code. And it is used to find out not just who is talking to whom, because we have that, but given a bunch of data that we know, what people are talking together, what they're talking about, we want to figure out where are the missing links. And we do that by treating the network as an adjacency matrix. The network graph can just be broken down into a matrix where each column is a node and each row is a node. And you can put zeros if they're not connected, ones if they are connected. Or you can maybe do an integer greater than 1 if they have multiple connections. And of course, you can treat this. You could use a hypergraph to do this instead, if in case a regular graph wasn't powerful enough. But now what we're trying to do is we're trying to fill in the blanks. If A is talking to B, what's C in between them? We can treat this like a recommendation engine. And we all know about the Netflix prize. This is over 10 years ago now, right? About 10 years ago. The team from Bell Labs with their partners won the Netflix prize with a revolutionary technique. And I am happy to say that the gentleman third from the right, Chris Walensky, comes to the meetup all the time. He's a regular member of the meetup, contributing back to the community. They came up with the novel use of non-negative matrix factorization to fill in the blanks. The general idea is that you take your giant matrix, which doesn't have to be people. It could be user item, user movie is what they were doing. It could be on the top, it's person, place, and thing, and exact same things on the side. You break that into two smaller matrices, which are approximations now. And when you multiply them back together into the original size matrix, you no longer have your ones and zeros or your integers. You now have probabilities. And it gives you a probability for how connected two different nodes are. And now you can judge whatever your cutoff is, if they're highly probable to be connected. You assume there was a missing edge that you couldn't observe, and you need to go investigate where this hidden person was. Now, they won the Netflix prize, and this was revolutionary. But now it's become almost ordinary. There is an R package called Recommender Lab that does it all for you. Just a few lines of code, you can do this. So it's really become quite simple and democratizing for us all to use. So what have we done today? What have we seen? We saw anomaly detection with simple linear models. We saw play-by-play football analysis using binary regression, boosted trees, and even neural networks. And we learned how to devise communication patterns with network analysis and matrix factorization. And it all comes down to having the right tools and remembering this Venn diagram. You have to know which part of AI to use. You have to have the right people, the right knowledge to do it. And then you need to know when to use the right tools to implement all of this. You do that, and you can accomplish really amazing things with ML and AI. And that really opens up the world and gives you an incredible amount of power. So thank you very much.